Assalamualaikum and greetings to all of you. In this video, we will discuss about a topic called differentiation. But before we start, let me introduce you to my teammates. So here we have Nur Kairinisa, Michelle, and me, Nur Natasha Irwayu. And we name our group as Pi Pals. Now, let us move to our topic for today. Have you ever heard about a differentiation before? Differentiation is a method of finding the derivative of a function that helps to solve many types of real-world problems. And these are the examples of problems that you might find in differentiation, such as cost, strength, the amount of material used in a building, profit and loss. And basically, you will meet them in engineering and science problems. After that, you also need to know the applications of differentiation. There are 5 of them. First is to finding the rate of change of a quantity. Second, the approximation value. Third, the equation of tangent and normal to curve. Fourth, the minimum and maximum of algebraic expression. And the last one is to determining the increasing and decreasing functions. That's all for the introductions of this topic. Now, let's see for the examples together.
As for the first question, I'm gonna explain to you how to answer a related rate question. The question states it is assumed that oil spilled from a ruptured tanker spreads in a circular pattern whose radius increases at a constant rate of 2 feet per second. How fast is the area of the spill increasing when the radius of spill is 60 feet? So, in order to answer this type of question, first thing first, you need to highlight the most important keywords given in the question. Based on the highlighted points, the oil spill spreads in a circular pattern, meaning that the formula that we need to include in our calculation is the formula of area of a circle, which is pi r squared. Next, take a look at the second point given, the constant rate, which is 2 feet per second. This shows that the distance from the center of the circle to its edge is growing constantly by 2 feet every second. This can be expressed as dr over dt equals to 2 feet per second, where r is the radius of the circle and dr over dt is the rate of change of the radius with respect to time. And the third point is the radius of the spill, which is 60 feet. Now, how do you answer this type of question? Let's take a look at the solution. In order to solve the question, you will need to separate the derivatives into two components, which are dA over dr and dr over dt. These components are the same value as dA over dt if you multiply them. And as we know, the formula of area of a circle is pi r squared. And the derivation of this formula will get you 2 pi r, which is equivalent to dA over dr. Now that we have both values for dA over dr and dr over dt, we can simply put these values into the initial equation. You will get dA over dt equals to 2 pi in brackets 60 times 2. Therefore, the answer would be 240 pi feet square per second. This indicates that the area of spill is 240 pi feet square per second when the radius is 60 feet.
The second problem statement is maximum and minimum problem. A closed-cylinder can is to hold 1 liter or 1,000 centimeter cube of liquid. How should we choose the height and radius to minimize the amount of material needed to manufacture the can? We are given the volume of the can, which is 1 liter or equivalent to 1,000 centimeter cube. Let us consider the radius of the cylindrical can is r and its height is h. The cost of manufacturing will be proportional to the total surface area of the can. First, The formula of volume is pi r square h. We know volume is equal to 1000 centimeter cube. Then we rearrange h equals to 1000 over pi r square. Secondly, the formula of total surface area of cylinder is 2 pi r square plus 2 pi r h. Then we substitute 1000 over pi r square into h. After that, we will get the total surface area of cylinder, which is equal to 2 pi r square plus 2000 over r. Thirdly, we will perform the derivative test to optimize the area function. From this, we will get negative 2000 over r square plus 4 pi r square equals to 0. We will move 2000 over r square to the side. After that, we will move 4 pi and cube to the side to find r. Finally, the value of r is 5.42 cm. Lastly, we will find the height h. H is equal to 1000 over pi r square. Substitute the radius into r. Thus, the height of the can is 10.84 cm.
In conclusion, the given problem of a radius increasing at a constant rate of 2 feet per second exemplifies the application of time rate change in real-world scenarios. One practical application of this concept is in determining the rate at which the area of an oil increases over the time, providing crucial information for environmental response strategies. Additionally, understanding the relationship between the height and radius of a container is essential for designing vessels that can hold specific volumes of liquid. By employing differentiation methods, we can solve both current and future problems involving changing dimension and rates, making these techniques invaluable for a wide range of scientific and engineering applications.
Before we end, these are the references that we have used in this topic. Thank you for your time and thanks for watching.